There is a cold silence underneath Canada that has lasted longer than memory, longer than any written record, longer than any civilization that has ever called this land home. Beneath the tundra of the Yukon, beneath the boreal forests of northern Manitoba, beneath the vast emptiness of the Northwest Territories and the frozen islands of the high Arctic, there exists a layer of earth that has not thawed since the last ice age. Scientists call it permafrost, and for tens of thousands of years it has done exactly what its name promises. It has stayed frozen. It has stayed permanent. It has held the world beneath Canada in a grip of cold that nothing and no one has been able to break. Until now, something is changing. The grip is loosening. And what is coming out of the ground as that ancient freeze releases is rewriting everything we thought we knew about this land, about the creatures that walked it, about the viruses that lived in it, and about the hidden history buried beneath the feet of everyone who has ever called Canada home. In the summer of 2022, a gold miner working a remote claim in the Yukon's Eureka Creek broke through a wall of frozen mud and exposed something that no living human had ever seen before. Curled against the earth, as perfectly preserved as the day it died, was the complete mummified body of a baby woolly mammoth. The fur was still attached, the skin was still intact. The tiny trunk, the little feet, the folds of the eyelids were all there, suspended in time, waiting to be found. The miner called her Nunchoga, a word from the local Trondek Hwechin, First Nation, meaning big baby animal. She was approximately 35,000 years old, and she looked like she had died last week. But Nunchoga is only the beginning of what is coming out. Before we go any further, if you are the kind of person who wants to understand what is really happening beneath the surface of this country, this is exactly the kind of content we make. Hit subscribe. Turn on notifications, because what comes next in this documentary is going to change the way you think about Canada, about history, about time itself, and about what we may have already accidentally unleashed from the deep freeze. The permafrost that underlies nearly half of Canada's land area is not simply frozen dirt. It is a time capsule of almost incomprehensible age. It is a library written in ice and soil containing specimens, organisms, viruses, DNA, gases, and evidence of ancient worlds that were sealed away before human civilization existed. It stretches beneath approximately 5.5 million square kilometers of Canadian territory. In some places, it reaches only a few meters below the surface. In others, it plunges hundreds of meters deep into the bedrock, a column of perpetually frozen material that has been locked in place since the Pleistocene epoch, the geological age of great glaciers and giant mammals that most people know only from museum exhibits and Hollywood films. Understanding what permafrost actually is requires letting go of the idea that frozen ground is simply cold dirt. The permafrost that exists beneath Canada is not frozen because of this winter's temperature. It is frozen because it has been accumulating cold for millennia. Each winter for tens of thousands of years, the surface of the ground froze. Each summer, the very top layer thawed briefly, maybe a few centimeters, maybe a few feet, in what scientists call the active layer. But below that active layer, the cold kept building, kept compressing, kept holding. Generation after generation of ice ages and cold periods stacked their chill into the earth until the ground beneath Canada became, in essence, a natural deep freezer, operating on a geological time scale. And like any freezer, it preserved whatever was placed inside it. Animals that died in the Pleistocene, that were swallowed by mudslides or fell into sinkholes, or simply collapsed into boggy ground at the edge of ancient rivers, were frozen before decomposition could take hold. Entire organisms, from microscopic bacteria and viruses to massive elephantine creatures, were encased in the permafrost and held there, suspended in biological stasis, waiting in the dark cold for someone or something to open the door. Canada's permafrost zone is not uniform. It exists in 3 broad bands that scientists describe as continuous, discontinuous, and sporadic permafrost. In the high Arctic and the far north, the permafrost is continuous, meaning it underlies the ground in an unbroken sheet with no gaps, covering the entire landscape from one edge to the other. Move south from there into the subarctic, and the permafrost becomes discontinuous, broken up by areas where it is absent, forming a patchwork beneath the boreal forest. Move further south still into the upper reaches of the prairie provinces and the northern edges of the settled territories, and the permafrost becomes sporadic, appearing only in isolated pockets wherever local conditions have allowed it to survive. It is this permafrost, in all 3 of its forms across Canada's north, that is now in serious, measurable, scientifically documented retreat. The numbers that researchers are working with are not subtle. Since systematic measurements began in the 20th century, ground temperatures across Canada's permafrost zones have risen by an average of 1 to 2 degrees Celsius. That sounds like almost nothing. It is not nothing. In a system that has been held at or near the freezing point for 20,000 years, a single degree of warming is catastrophic. It is the difference between ice and water. It is the difference between locked and released. It is the difference between a library sealed in frozen stone and a library dissolving into mud. The warming is not happening evenly. The Canadian North is warming at roughly 3 times the global average rate. The Arctic, the coldest and most remote part of the country, is warming even faster than that. Temperature records that were once considered permanent benchmarks are being broken year after year. Sea ice that once covered the Arctic Ocean for most of the year is now retreating earlier in spring and returning later in fall, exposing dark ocean water that absorbs solar heat, rather than reflecting it, which then warms the surrounding land, which then further thaws the permafrost, which then releases carbon that further warms the atmosphere, which then continues to accelerate the entire cycle. This feedback loop is one of the most alarming things in all of contemporary climate science, and it is centered directly on Canada. But the warming of the permafrost is not only a story about the future, it is also, urgently and irreversibly, a story about the past, because as the permafrost melts, it is releasing its contents. Everything that was stored in that ancient deep freeze is coming out now. Some of it is breathtaking, some of it is beautiful, some of it is scientifically perfectly invaluable, and some of it, according to researchers who study ancient microbes and prehistoric pathogens, is genuinely, measurably dangerous. To understand what is coming out of Canada's permafrost, it helps to understand what went into it. The period of time that the permafrost primarily preserves is the late Pleistocene, an era spanning roughly from 100,000 years ago to approximately 10,000 years ago. During the height of that epoch, the landscape that is now Canada's north looked nothing like what exists there today. Large portions of what is now the Yukon and Alaska were not covered by glaciers. Instead, they formed a biological refuge called Beringia, a vast, cold, but biologically rich grassland ecosystem that served as a land bridge between Asia and North America and as a haven for one of the most extraordinary assemblages of large animals the world has ever seen. Beringia was home to woolly mammoths, woolly rhinoceroses, giant ground sloths, American camels, ancient horses, ancient bison, cave lions, scimitar-toothed cats, short-faced bears, steppe wolves, and dozens of other species that are now entirely extinct. It was a world so different from the Canada of today that if you could step back into it, you would not recognize the landscape or the ecology. The grasses that grew there were dense and nutritious, capable of supporting enormous herds of megafauna. The sky above was cold and clear. The predators were creatures of nightmare. And all of it, every animal that died and was buried and preserved in that ancient ground, is now potentially available to the scientists and the miners and the ordinary Canadians who are digging through the thawing earth. Nuncho-Ga, the baby mammoth found in the Yukon in 2022, is perhaps the most famous of these discoveries, but she is far from the only one. In 2020, Yukon miners working at a placer gold mine near the town of Dawson City uncovered the nearly complete remains of an ancient horse. The discovery was exceptional, not only for its preservation, but for what the DNA extracted from it revealed. The horse was approximately 40,000 years old, and it belonged to a lineage of horses that predated the modern horse by tens of thousands of years. Analysis of its genome has helped scientists understand the evolutionary history of horses in North America and their relationship to the horses that later spread across Asia and Europe after being domesticated roughly 5,000 years ago. The same Yukon goldfields have produced an extraordinary range of Pleistocene fauna over the decades since placer mining began in the region. Woolly mammoth tusks, teeth, and bones appear regularly in the tailings of mining operations. Ancient bison skulls emerge from the melting cut banks along rivers. The bones of cave lions, animals that were larger than any living lion and ranged across the entire northern hemisphere during the Pleistocene, have been found in multiple locations across the Yukon. Fragments of woolly rhinoceros, an animal that most people associate exclusively with Siberia, have occasionally turned up in Canadian permafrost sites as well, evidence that this enormous, armored, shaggy beast ranged much further into North America than the textbooks have traditionally suggested. Perhaps the most extraordinary individual specimen to emerge from the Canadian permafrost before Nuncho-Ga was a creature known informally as Yukon gold. Discovered in the 1990s, this mummified specimen of an ancient steppe bison was preserved well enough that scientists were able to examine its muscle tissue, its skin, and its internal organs in detail that would be impossible with ordinary fossilized bone. What they found confirmed what they had long suspected from Siberian specimens of the same type, that these ancient bison were physiologically distinct from their modern descendants, in ways that suggested they were adapted to the cold, dry grasslands of Beringia in highly specific ways that modern plains bison are not. These animals are not fossils in the traditional sense. Fossils are mineralized, replaced over millions of years by stone, their original organic material long since dissolved and rebuilt as rock. What is coming out of Canada's permafrost is something different. It is genuine biological tissue, real DNA, real proteins, real cellular material that can be extracted, sequenced, analyzed, and in some cases, theoretically, reactivated. That last word is where things get uncomfortable. The conversation about ancient DNA recovered from permafrost specimens has been ongoing in the scientific community since the 1980s, when researchers first demonstrated that usable genetic material could be extracted from ancient biological remains. Over the following decades, the techniques have become progressively more sophisticated, the specimens progressively more intact, and the questions progressively more serious. When a species is preserved in permafrost with enough biological fidelity that its entire genome can be sequenced, the theoretical question of whether that species could be brought back from extinction moves from the domain of science fiction into the domain of genuine scientific debate. The woolly mammoth is the central subject of that debate. Several companies and research groups are currently working towards some version of mammoth de-extinction, using the genome of the Asian elephant, the mammoth's closest living relative, as a base, and editing it to incorporate mammoth-specific genetic traits. The Canadian permafrost, as one of the world's richest sources of intact mammoth DNA, plays a direct role in this effort. Every new specimen like Nuncho Gay potentially provides fresh genetic data to fill in the gaps in the mammoth genome and move the de-extinction project closer to reality. But the mammoth is not what keeps the specialists in ancient microbiology awake at night. What concerns them is something far smaller, far older, and in some ways far more resilient than any megafaunal specimen. What concerns them is the ancient microbial world that was also sealed into the permafrost alongside the mammoths and the bison and the ancient horses. Bacteria, fungi, viruses, and other microscopic organisms that lived and died in the ancient soils of Beringia were also preserved when those soils froze. And unlike the megafauna, which are visibly extinct and clearly separate from the living world, ancient microbes and viruses occupy a much more ambiguous biological territory. In 2023, a team of European researchers published results that sent a quiet shock through the scientific community. Working with permafrost samples drawn from Siberia, they had successfully revived multiple ancient viruses that had been frozen for tens of thousands of years. The oldest of these, a virus they named Pandora virus Yedoma, had been dormant in the frozen ground for approximately 48,500 years. When it was thawed and introduced to cultured cells in a laboratory setting, it reactivated. It began to replicate. It infected the host cells and spread through the culture as efficiently as any modern virus. The viruses successfully revived in that study were chosen specifically because they infect amoeba, not humans. The researchers were not reckless. They understood that working with unknown ancient pathogens required extreme caution, and that using amoeba-infecting viruses allowed them to study reactivation without any risk of infecting human research staff. But the demonstration that an organism could survive nearly 50,000 years of frozen storage and emerge from the permafrost functionally capable of infecting living cells was not a trivial finding. It was, in the words of one of the researchers involved, a proof of concept that should be taken very seriously. The question that followed immediately was this: if harmless amoeba infecting viruses can survive 50,000 years in permafrost and reactivate when thawed, what else might survive? What other pathogens are locked in the frozen ground of the north, waiting for the temperature to cross the threshold between frozen and unfrozen, between dormant and active? Canada's permafrost is as old as Siberia's. The Yukon's Beringian deposits are in some areas directly continuous with the Siberian deposits across the shallow seabed of what was once the Bering Land Bridge. The ancient soils that froze in Canada froze at approximately the same time, under approximately the same conditions, and have been held at approximately the same temperatures as the Siberian soils where the ancient viruses were found. There is no scientific reason to believe that Canada's permafrost contains anything fundamentally different from what Siberia's permafrost contains in terms of ancient microbial life. This is not a theoretical risk reserved for distant future scenarios. The permafrost in Canada is thawing now. The active layer, the thin zone of soil above the permafrost that thaws each summer and refreezes each winter, is deepening. What was permafrost last decade is active soil this decade. What is active soil this decade may be standing water next decade as the ground collapses into thermokarst. Thermokarst is one of the most visually striking and least understood consequences of permafrost thaw. When the ice that is mixed through the permafrost melts, the ground above it loses its structural support. The soil settles, subsides, and collapses in irregular patterns that create a landscape of humps and hollows, ponds and sinkholes, tilted trees, and sinking buildings that looks nothing like the solid level terrain that was there before. Scientists call this drunken forest when it happens in treed areas, because the trees, their root systems suddenly deprived of solid footing, lean in random directions as the ground shifts beneath them. In open areas, the thermokarst process creates what are called thermokarst lakes, pools of water that form in the depressions where the ice-rich permafrost has melted away. These thermokarst lakes are appearing across Canada's north at a rate that has surprised even the researchers who predicted their expansion. Satellite imagery of the Yukon, the Northwest Territories, and Nunavut shows new lakes and ponds appearing in areas that were solid ground just decades ago. Old lakes are growing larger as their banks collapse into them. Some lakes eventually drain catastrophically when the permafrost dam holding their water gives way, leaving behind raw exposed permafrost surfaces that release enormous quantities of both carbon dioxide and methane directly into the atmosphere. The methane story is the one that worries climate scientists most. The organic material stored in permafrost, the bodies of ancient animals, the roots of ancient plants, the ancient soils that built up over tens of thousands of years, is rich in carbon. When that material was frozen, it was prevented from decomposing. It was chemically arrested, held in a state of suspended organic chemistry that could not proceed because the temperatures were too low for the microbial processes of decomposition to operate. But when the permafrost thaws, that organic material is suddenly available to the microbes that are newly active in the warm soil. Those microbes begin to break it down, and as they do, they release that stored carbon in two forms. In well-drained, oxygenated conditions, they release it as carbon dioxide. In waterlogged, oxygen-poor conditions, which is what the thermokarst lakes and bogs of the thawing permafrost create, they release it as methane. Methane is a greenhouse gas roughly 80 times more potent than carbon dioxide over a 20-year time frame. The permafrost of the Arctic and subarctic is estimated to contain approximately 1.5 trillion tons of organic carbon, roughly twice the amount currently present in the entire atmosphere. Even the partial release of that carbon store into the atmosphere would have consequences for the global climate system that are difficult to overstate, and the thawing of Canada's permafrost is making that partial release a present reality rather than a future possibility. The craters are perhaps the most dramatic physical manifestation of what is happening. Beginning in 2014, large holes began appearing in the Yamal Peninsula of Siberia, perfectly circular depressions dozens of meters across and tens of meters deep, with steep sides and no obvious cause. Initial speculation ranged from meteorite impacts to underground explosions. The actual explanation was more unsettling. Beneath the Siberian tundra, pockets of methane gas had been building up under pressure as the permafrost above them slowly weakened. When the pressure became sufficient, the cap of permafrost above the gas pocket blew outward in an explosion powerful enough to hurl chunks of frozen earth hundreds of meters. The result was a perfectly circular crater, empty at the bottom with the ejected material scattered in a ring around the rim. Variations of this phenomenon have been documented in Canadian territory as well. While the dramatic, sudden explosions seen in Siberia have not yet been observed in Canada to the same degree, researchers monitoring northern Canadian permafrost have identified numerous areas where the ground is literally bubbling. Methane that has accumulated beneath thin layers of weakening permafrost is pressing upward, creating raised mounds called pingos and palsas that can be meters high, and in some documented cases, piercing the surface to release gas that can be ignited with a match. Videos of researchers setting fire to the ice-covered surface of northern lakes, producing dramatic flares from the methane seeping up through the ice, have circulated widely online, offering a vivid and slightly alarming demonstration of what is happening beneath the ground. The human infrastructure of northern Canada is absorbing the consequences of permafrost thaw in ways that are already being counted in hundreds of millions of dollars, and that will eventually be counted in billions. The buildings, roads, airstrips, pipelines, and other infrastructure of Canada's northern communities were almost universally built on permafrost that was assumed to be stable. It was not a naive assumption. For most of recorded Canadian history in the north, the permafrost had been stable. Buildings constructed in the 1950s and 1960s in places like Inuvik, Norman Wells, and Yellowknife were built on permafrost that engineers had every reason to believe would remain frozen for centuries. The buildings were engineered to sit above the ground on pilings to avoid transferring heat from the building into the permafrost and causing local thaw. For decades, the system worked. Now, the problem is not the heat from the buildings. The problem is the heat from the air itself. The permafrost is warming from above, from below, and from the sides simultaneously. Buildings that were level and stable a generation ago are now tilting, cracking, and subsiding as the frozen ground beneath their foundations softens. Roads that were straight are now heaving into roller coaster curves as the permafrost beneath them shifts. Airstrips that served as the lifeline for remote communities are being resurfaced and regraded at enormous expense as the underlying ground becomes unreliable. Pipelines that carry oil and natural gas across the northern landscape are under constant scrutiny as the ground they pass through changes shape. The community of Inuvik in the Northwest Territories, a planned town built in the late 1950s, specifically to accommodate the challenges of construction on permafrost, is now dealing with permafrost problems that the original engineers never anticipated and for which the infrastructure they built provides no solution. Municipal buildings are being demolished and rebuilt. The water and sewer system, which runs above ground in insulated utilidors, rather than below ground precisely because the ground was considered too unstable for underground infrastructure, is now facing new challenges as even the surface conditions change. The famous utilidor system, once a point of local pride and a clever engineering solution to an extreme environment, is becoming a source of ongoing maintenance challenges as the ground beneath it continues to shift. For the Indigenous peoples who have lived on Canada's northern permafrost lands for thousands of years, the changes are not just an infrastructure problem. They are a transformation of a landscape that has been the foundation of a way of life, a source of food, a navigational reference, and a spiritual home for a span of time that dwarfs the brief period of European contact. The Trondek-Hwetchin people of the Yukon, whose territory encompasses much of the Dawson City region, where many of the most spectacular permafrost discoveries have been made, have deep cultural knowledge of the land that is now being disrupted. Elders in northern communities across Canada describe changes to the land that match what the scientific instruments are recording, but that they have been observing through their own experience and through the accumulated experience of their communities over generations. The trails that were solid in winter are now soft in places where permafrost has gone. The ground that was reliable for travel by snowmobile or dog sled has in some areas become treacherous. Lakes that were full are draining. Rivers that ran in one channel have shifted. The timing of the seasons themselves has changed in ways that affect the animals and the plants that the northern Indigenous peoples have relied on since before Canada existed as a country. The knowledge held in Indigenous communities about northern landscapes is itself a form of historical record that is increasingly relevant to scientists studying permafrost change. Traditional ecological knowledge, the accumulated observations of generations of hunters, fishers, harvesters, and travelers who lived intimately with the northern landscape, often encodes information about environmental change that predates any scientific monitoring. When elders describe how a particular lake used to be shallow and is now deep, or how a particular slope used to be accessible in summer and is now a bog, they are describing decades of change that no instrument recorded because no instrument was there. That knowledge is now being sought by researchers who understand that the scientific record of permafrost change extends back only a few decades, and that understanding the full scope of what is happening requires every source of information available. The Inuit peoples of Nunavut and the Northwest Territories have particular and long-standing knowledge of sea ice and coastal permafrost conditions. Their testimony about changes to sea ice, extent, thickness, and timing, now extensively documented by researchers working in partnership with northern communities, is consistent with, and in many cases antecedes the satellite data that began to be collected systematically in the 1970s. When Inuit hunters say that the sea ice is behaving differently from the way it behaved in their grandfather's time, they are not speaking metaphorically. They are describing specific changes in specific locations over a span of time that no scientific instrument monitored. The permafrost of northern Canada also contains a different kind of historical record, the physical remains of the people who lived there in the ancient past. Human remains have been found in permafrost contexts in Canada, though they are far less numerous than the animal specimens and represent only specific circumstances where bodies were preserved in frozen conditions. The most famous Canadian permafrost human find is not a prehistoric individual, but a historical one. In 1845, the British Royal Navy expedition commanded by Sir John Franklin sailed into the Canadian Arctic in search of the Northwest Passage and vanished. All 129 men eventually died, and the circumstances of their deaths remained one of the great mysteries of Arctic exploration for more than a century. In 1984, a team of researchers led by Owen Beatty of the University of Alberta exhumed the bodies of 3 Franklin expedition sailors who had been buried on Beechey Island in the high Arctic. The burials were in permafrost. The bodies were preserved with extraordinary completeness, the faces of men who had been dead for 139 years still recognizable, their skin and hair intact, their clothing still buttoned. Forensic examination of the bodies revealed elevated levels of lead in their tissues, almost certainly from the lead solder used to seal the expedition's tinned food cans. This lead poisoning, combined with the nutritional consequences of the failing food supply and the brutal conditions of the Arctic, likely played a significant role in the expedition's catastrophic collapse. The Franklin discovery demonstrated in the most direct possible way what the permafrost of the Canadian Arctic is capable of preserving. These were not ancient specimens from a vanished geological era. They were historical human beings, men whose names were known, whose families had lived and died in their absence in Britain, whose fate had haunted the British public for decades. And the permafrost had kept them intact as if they had been buried only weeks before. If the permafrost can preserve a 19th century sailor in near-perfect condition for 139 years, the question of what else it might be holding from deeper in human history is not idle speculation. There is growing evidence that the Canadian Arctic and subarctic were inhabited by human populations much earlier and more extensively than the conventional historical account suggests. The traditional narrative of North American human settlement, which held that people first entered the continent via the Bering Land Bridge approximately 13,000 years ago and spread southward from there, has been under sustained revision for the past 3 decades as new archaeological evidence has accumulated. Sites in the Yukon, including the Old Crow Basin and Bluefish Caves, have produced evidence of human presence dating to at least 24,000 years ago and possibly earlier. The Bluefish Caves excavated primarily in the 1970s and 1980s, yielded animal bones bearing what appear to be cut marks made by stone tools, suggesting that humans were present in what is now the Yukon during a period when the conventional timeline of North American settlement would have them still on the Asian side of the Bering Land Bridge. The age and interpretation of these marks has been debated, but recent reanalysis using improved dating techniques has supported the earlier settlement dates. The implications of an earlier human presence in Canada's north are significant not just for the abstract question of when people arrived in North America, but for the more immediate question of what the permafrost might preserve from those early occupations. If humans were living in Beringia, that's 24,000 years ago, they left behind evidence of that life. Tools, hearths, food, remains, and eventually, bodies. Some of that evidence is on the surface in archaeological sites, but some of it is in the permafrost, sealed away in the same frozen matrix that has preserved the woolly mammoths and the ancient horses, waiting for the moment when the thaw will expose it or the climate change will destroy it before it can be found. The race between discovery and destruction is one of the most urgent dynamics in Canadian permafrost. Archaeology today. The same warming that is bringing these ancient materials to the surface is also, once they reach the surface, exposing them to the processes of decomposition that the permafrost had been holding at bay. A mammoth tusk that emerges from a thawing cut bank and lies on the surface in the summer sun begins to crack within weeks. Organic specimens that have been frozen for 30,000 years can deteriorate within a single season once they are exposed to air and warmth. Specimens of bone, wood, and other organic material that would be priceless to science if they could be studied properly are instead degrading in place before researchers can reach them. This is particularly true in areas where permafrost thaw is happening rapidly and where the nearest scientific institutions are thousands of kilometers away. The remote mining regions of the Yukon, where the most spectacular frozen specimens have been found, are not close to university, laboratories, or natural history museums. When a miner breaks through a wall of frozen ground and finds a mammoth, the practical question of how to preserve it, document it, and get it into the hands of scientists before it degrades is often answered inadequately. Many specimens are lost to decomposition or damaged beyond scientific utility before anyone with the relevant expertise can examine them. The collaboration between the Yukon government, First Nations communities, and scientific institutions to address this problem is ongoing and imperfect. Guidelines exist for what miners are supposed to do when they discover permafrost specimens. There are reporting requirements and protocols for site preservation, but the remote, dispersed, and often unmonitored nature of placer gold mining in the Yukon makes consistent enforcement of these guidelines difficult. The honest acknowledgement within the scientific community is that an unknown number of significant specimens have already been destroyed or damaged in the process of gold extraction before anyone knew they were there or had any chance to study them. The ancient forests emerging from Canada's permafrost tell a different kind of story from the animal remains. On Ellesmere Island, in the Canadian High Arctic, researchers have documented what may be the most surprising of all the permafrost's hidden contents. The preserved remains of ancient forests that grew there during a period when the Arctic was dramatically warmer than it is today. The stumps, logs, and leaf litter of these forests, preserved in permafrost for millions rather than thousands of years, are evidence of a world so different from the modern Arctic that it seems to belong to a different planet. The forests of ancient Ellesmere, which grew during the Eocene epoch, approximately 45 to 53 million years ago, were warm temperate to subtropical in character. The trees included species related to modern sequoias, dawn redwoods, and bald cypresses, trees that today grow in much warmer climates far to the south. The ancient Arctic forest grew in an environment where the sun did not rise for months in winter and did not set for months in summer, an environment with no modern analog, and it thrived. The preservation of this forest in the permafrost of Ellesmere Island has given scientists a uniquely detailed picture of what the Arctic looked like tens of millions of years ago, and a sobering reminder of how dramatically the climate of this region has varied over geological time. The ancient Eocene forests of Ellesmere are not, of course, at risk of reactivation in the way that the ancient microbes are. 50-million-year-old plant material does not contain viable organisms, but what these ancient forests represent is something almost as significant. Evidence that the Arctic has experienced extreme warming before has supported ecosystems radically different from those that exist there today, and that the permafrost, which underlies the modern Arctic, is not a permanent feature of the landscape, but a product of specific climatic conditions that have existed only briefly in geological terms and may be ending now. Closer to the Holocene, the epoch of human civilization, the permafrost has preserved evidence of forests that are more recent and more directly relevant to the historical ecology of Canada. Across the northern boreal zone, thawing permafrost is exposing the stumps and root systems of ancient trees in areas that are currently treeless tundra. These ancient trees, carbon dated to thousands of years ago, grew in areas that were then warm enough to support forest cover, were killed by a cooling climate that formed the permafrost, and have been frozen in place ever since. Their emergence as the permafrost thaws now is a kind of ecological time travel, the visible remnant of a forest that stood before any European had ever seen this land. The tree line, the northern limit of boreal forest, is itself moving northward as the permafrost thaws and the climate warms. Scientists monitoring the tree line across Canada's subarctic have documented its gradual advance into territory that was previously tundra, as spruce and other cold-tolerant trees colonize the newly thawed and drier ground. This tree line advance has been happening for decades and is accelerating. It represents a fundamental reorganization of Canada's northern ecosystems, one that will eventually transform the landscape of the country's north in ways that are difficult to predict in detail, but easy to recognize in principle as dramatic and irreversible. The wildlife of Canada's north is responding to permafrost thaw in ways that are already reshaping the ecology of the region. Caribou, whose great seasonal migrations across the tundra have been a defining feature of northern Canada's natural heritage for thousands of years, are facing disruptions to their migration routes as the landscape changes. Rivers that were reliable crossing points are shifting. Ground that was solid enough to support caribou hooves in summer is becoming boggy and treacherous. The timing of the green up of tundra vegetation, on which the caribou depend for the nutritional peak of their summer grazing, is shifting in ways that may or may not align with the timing of the caribou's migratory arrival. Polar bears, whose habitat is the sea ice of the Canadian Arctic, are facing a permafrost-adjacent crisis driven by the same warming that is thawing the land ice. The sea ice on which they hunt, travel, and rest is declining in extent and duration every year. Polar bear populations that were once among the most robust in Canada's Arctic are now classified as vulnerable, and the populations that depend on the most dramatically retreating sea ice are in serious decline. The warming that is thawing Canada's permafrost and the warming that is melting Canada's sea ice are the same warming, driven by the same forces, and producing in parallel the thawing of the ancient frozen library and the degradation of the living Arctic ecosystem that depends on the cold. The question of what should and should not be emerging from Canada's permafrost is not only a scientific or ecological one. It carries a weight of historical and political meaning that is difficult to separate from the facts of the thaw. Canada's north and the permafrost that underlies it is not empty space waiting to be discovered. It is Indigenous territory. It is home. It is a landscape that has been lived in, depended on, and cared for by First Nations, Métis, and Inuit peoples for at least as long as the most ancient specimens now emerging from the ground have been frozen. The permafrost and its contents are not simply scientific resources to be extracted and studied. They are embedded in a web of relationships, rights, and responsibilities that require a fundamentally different approach from the one that characterized 20th century science in the North. The Trondek Hwetchen, First Nations' role in the response to the discovery of Noon, Cho Ga, the baby mammoth, illustrates what that different approach looks like in practice. Rather than the specimen being immediately shipped to a southern laboratory for study, the process involved extensive consultation with Trondek Hwetchen, leadership, and the application of the nation's own cultural protocols to the handling of the remains. The name given to the mammoth was not chosen by scientists, but by Trondek Hwetchen elders. The significance of the discovery was interpreted not only through the lens of paleontology, but through the lens of the First Nations' relationship with the land and with the creatures that had lived on it in ancient times. This approach, imperfect and still evolving, represents a significant departure from the historical pattern of scientific extraction without community consultation that characterized most of the 20th century's engagement with the archaeology and paleontology of Canada's north. The ancient viruses recovered from permafrost have also raised ethical questions that extend beyond the purely scientific. If viable pathogens are present in the permafrost that is now thawing, the question of who has the right to study them, under what conditions, and with what safeguards is not merely procedural. The history of the introduction of new pathogens into indigenous communities in North America, going back to the earliest period of European contact, is one of catastrophic disease and depopulation. The idea that the thawing permafrost might release ancient pathogens into environments where northern indigenous peoples live is not an abstraction. It is a question with direct implications for living people whose communities are in the path of the thaw. The scientific consensus on the risk from ancient permafrost pathogens is nuanced rather than alarmist, but is not reassuring. The viruses that have been successfully revived from Siberian permafrost are, as noted, amoeba, infecting viruses without known ability to infect humans. But the reason researchers chose to work with those particular viruses is precisely that their host range was known to be safe. The permafrost contains enormous diversity of ancient microbial life, most of it unstudied and uncharacterized. The majority of ancient viruses in the permafrost are likely harmless to humans because most viruses are specific to their host species, and the hosts of most ancient viruses are not humans. But the possibility that pathogens capable of infecting humans or animals that are in close contact with humans might be present in the permafrost and might be released by thawing cannot be ruled out. The most cited specific risk is ancient smallpox, or pox viruses more broadly. Smallpox was eradicated in 1980, and the only official stocks of variola, the smallpox virus, exist in 2 approved repositories, one in the United States and one in Russia. But the history of smallpox in North America predates European contact, and the remains of people who died of smallpox are present in the permafrost of the north. Some researchers have argued that viable smallpox or related pox viruses might be preserved in frozen human remains from communities devastated by smallpox epidemics in the historical period. This is considered a low probability risk by most specialists, partly because pox viruses are not as durable as certain other classes of pathogens, but it is not considered zero. Beyond smallpox, the concern extends to what researchers call unknown unknowns, pathogens that we have no record of and no immunity to, that may have circulated in the animal or human populations of ancient Beringia and have been sealed in the permafrost since they disappeared from the living world. The immune systems of modern humans are not naive. We carry within us the evolutionary legacy of countless exposures to pathogens over hundreds of thousands of years of human history. But that evolutionary record is not complete. There are diseases that circulated in ancient populations that we have no immunity to, because they disappeared before modern humans were exposed to them in sufficient numbers to drive the evolution of immune defenses. Bringing those pathogens back into contact with a modern human immune system that has no experience of them is not a scenario that anyone can fully predict. The science of ancient DNA has itself produced findings that blur the boundary between extinct and present. In recent years, analysis of ancient human genomes extracted from permafrost specimens and from the remains of individuals from archaeological sites across the Arctic and subarctic has revealed patterns of population movement, replacement, and interaction in the deep history of Canada's north that are far more complex than any previous model suggested. The ancient peoples of the American Arctic were not a single continuous population descending from the first humans to cross the Bering Land Bridge. They were a succession of distinct peoples, each with their own culture and technology, each moving into and across the Arctic in response to changing conditions, and each in some cases apparently replaced by the next wave of arrivals rather than being incorporated into the populations that followed. The Paleo-Eskimo cultures, which occupied the eastern Arctic of Canada from approximately 4,000 to 700 years ago, appear to have been genetically distinct from both the people who preceded them and the people who followed them. Their DNA, extracted from permafrost preserved remains at archaeological sites across the Canadian Arctic, shows that they were not the direct ancestors of modern Inuit. They were a separate people who lived in the Arctic for more than 3,000 years and then disappeared from the genetic record, apparently replaced rather than absorbed by the ancestors of the modern Inuit who moved into the eastern Arctic approximately 1,000 years ago. The reasons for this replacement are unclear. Climate change, competition for resources, and epidemic disease have all been proposed. What is clear is that the Canadian Arctic has a human history that is both older and more turbulent than the conventional account suggests, and that the permafrost is the primary physical archive of that history. The gold that drew European and then Canadian miners into the Yukon in the late 19th century played a complicated role in the scientific story of the permafrost. The Klondike Gold Rush of 1896 to 1899 brought tens of thousands of people to the Yukon and established the placer, gold mining industry that continues to operate there today. Placer mining, which involves washing gold-bearing gravel with high-pressure water to separate the heavy gold particles from the lighter sediment, inevitably cuts through permafrost when the gold-bearing gravels are buried beneath it. In doing so, it has exposed an enormous quantity of Pleistocene material that would otherwise remain frozen and inaccessible. The scientific value of the fossil and paleontological material discovered by Yukon placer miners over the past century is genuinely enormous. The collections at the Yukon Beringia Interpretive Center in Whitehorse represent only a fraction of what has been found in the goldfields. University museums across Canada and internationally hold significant collections of Pleistocene fauna from the Yukon mines. Individual specimens of exceptional quality have been sold to private collectors, which is legal under current Canadian law for certain categories of specimen and is a matter of ongoing controversy among paleontologists and First Nations communities who argue that these specimens are part of a shared natural heritage that should be publicly held. The relationship between the gold mining industry and the scientific community in the Yukon has not always been harmonious. Miners who discover paleontological specimens on their claims are required to report them to the territorial government, but the practical reality of a remote mining operation, where every day of delay in the mining season represents real financial cost, creates pressure to keep the operation moving, rather than stop for what the miner might perceive as fossils in the gravel. The education of the mining community about the significance of permafrost specimens and the development of efficient protocols for specimen retrieval that minimize disruption to ongoing mining operations has been a sustained effort of the Yukon government and scientific institutions for decades. It has produced real improvements in the relationship, but has not eliminated the tension between economic and scientific priorities. The economy of Canada's north is itself being reshaped by permafrost thaw in ways that cut across the interests of different communities in contradictory directions. For the mining industry, permafrost thaw creates both opportunities and challenges. The thawing of permafrost in areas that were previously inaccessible is in some cases revealing or making more accessible mineral deposits that were hidden beneath the frozen ground. At the same time, the infrastructure challenges associated with permafrost thaw, particularly the instability of roads and buildings, increase the costs of northern operations. For the oil and gas industry, the permafrost that underlies much of the Canadian North has always been both a resource and an engineering challenge. The methane that is now being released naturally from thawing permafrost is the same methane that the industry has been extracting commercially, and the thaw is changing the landscape in which pipelines and wellheads operate. For northern communities, the economic consequences of permafrost thaw are primarily negative in the near term and deeply threatening in the longer term. The cost of repairing and replacing infrastructure is being borne at the municipal and territorial level, with inadequate support from federal sources. The disruption of traditional subsistence activities, including hunting, trapping, and fishing, represents both cultural loss and real economic impact for communities that have not been fully integrated into the cash economy and that continue to depend on the land for a significant portion of their food supply. The psychological impact of watching a landscape that has been home and sustenance for generations transform into something unrecognizable is a form of harm that does not appear in economic statistics, but is consistently described by northern Indigenous peoples as one of the most significant consequences of what is happening. The broader Canadian public's awareness of what is happening in the permafrost north is limited in ways that have real consequences for policy and funding. Canada's north is vast but sparsely populated. The communities directly affected by permafrost thaw are small in population, remote in location, and consistently underrepresented in national media and political discourse. The dramatic specimens that emerge from the permafrost, the baby mammoths and ancient horses, attract international scientific attention and occasional viral media coverage, but the systemic story of infrastructure collapse, ecosystem transformation, and ancient pathogen risk does not command the sustained national attention that its scale and significance warrant. This is partly a function of geography. Most Canadians live in a narrow band along the southern border of the country, in a climate where permafrost is not present and where the consequences of its thaw are not directly felt. The idea that something profound is happening beneath the ground of a territory that most Canadians will never visit is difficult to make feel urgent and immediate. The political challenge of directing national resources toward a problem that is both genuinely serious and genuinely distant from the lived experience of most voters has been only partially met by successive Canadian governments, which have funded some research and some infrastructure adaptation, but have not treated permafrost thaw as the national priority that the scale of the problem suggests it should be. The international dimensions of Canada's permafrost situation complicate the domestic policy picture. Permafrost thaw is a global phenomenon occurring across the entire circumpolar north, in Russia, Alaska, Greenland, Scandinavia, and the high mountain permafrost zones of Asia and South America. The carbon that is being released from Canada's thawing permafrost joins the carbon from Siberia's thawing permafrost and contributes to the same global atmospheric concentration that is warming the climate everywhere. Canada cannot solve the permafrost problem alone, and the countries that are most directly contributing to the warming that is causing the thaw are not always the same countries that are bearing the consequences. Russia, which has by far the largest permafrost territory of any country, and which is experiencing some of the most dramatic permafrost changes, is both a major emitter of greenhouse gases and a country whose scientific research on permafrost is substantial and important. The long tradition of Soviet and then Russian research on permafrost science, conducted from permanent monitoring stations scattered across the vast Siberian landscape, provides some of the longest instrumental records of permafrost temperatures in existence. The degradation of this monitoring network during the economic chaos of the 1990s represented a genuine loss of scientific continuity. The rebuilding of monitoring capacity in Russia and the sharing of data between Russian, Canadian, American, and other circumpolar nation researchers is an ongoing effort that crosses geopolitical divides in ways that reflect the genuinely global nature of the problem. The scientific infrastructure that Canada has built for monitoring its permafrost, while substantial, is still inadequate to the scale of the territory and the rate of change. The Canadian Permafrost Association, university research programs at institutions including the University of Calgary, the University of Alberta, and Carleton University, and federal research programs through the Geological Survey of Canada and Environment and Climate Change Canada produce significant bodies of research. But the monitoring network remains far less dense than what would be needed to comprehensively document what is happening across 5.5 million square kilometers of permafrost territory. There are vast areas of Canada's north where the permafrost is changing without any systematic monitoring, where specimens are emerging and degrading without anyone knowing, and where the ground itself is transforming in ways that will only become visible to science long after the transformation has occurred. Remote sensing technology, including satellite-based radar and optical imagery, has partially compensated for the limitations of ground-based monitoring. The ability to observe changes in the land surface from orbit, to detect the formation of new thermokarst lakes, the emergence of new methane seep areas, and the subsidence of ground that indicates thaw at depth, has been transformative for the study of permafrost at landscape scales. Canadian and international satellites provide regular coverage of the country's permafrost zones that would have been unimaginable a generation ago. But remote sensing cannot see below the surface. It cannot detect the microbial changes happening in the thawing soil or the accumulation of gas pressure in the pockets where methane is building toward a crater-forming explosion. For those questions, there is no substitute for instruments in the ground and scientists examining the physical material. The specimens emerging from Canada's permafrost are also becoming increasingly significant in a geopolitical sense. The question of who owns the genetic information contained in a mammoth genome or an ancient virus, or the DNA extracted from ancient human remains, is not settled. International agreements on biodiversity and genetic resources do not straightforwardly apply to specimens extracted from permafrost, particularly when those specimens belong to species that are entirely extinct and have no living community whose interests must be consulted. The commercial potential of ancient DNA, which extends to pharmaceutical applications, biotechnology, and de-extinction projects, means that there are economic interests at stake in these specimens that go well beyond academic science. The legal framework for managing these interests in Canada as elsewhere lags far behind the scientific and commercial possibilities. The de-extinction projects that center on the woolly mammoth and that depend heavily on the DNA extracted from Canadian and Siberian permafrost specimens represent one of the most ethically and ecologically complex proposals in contemporary biology. The argument for bringing back the mammoth or a mammoth-like creature with sufficient mammoth genetic characteristics to fill the ecological role that the mammoth played in the Pleistocene steppe ecosystem has been made with increasing sophistication by researchers, including George Church at Harvard and the team at Colossal Biosciences. The ecological argument holds that the mammoth was a keystone species whose grazing and trampling of the steppe maintained the ecosystem in a state that was productive and that kept the permafrost colder and more stable than it would be without that pressure. The idea, which is being tested at a small scale at a site in Siberia called Pleistocene Park, is that reintroducing large grazing animals to the Arctic tundra and allowing them to compact the snow, disturb the soil, and graze the vegetation, in the patterns that megafauna historically maintained, would preserve the permafrost by reducing its warming. The snow compaction effect, in particular, is supported by research suggesting that the presence of large animals that break up and compact the insulating snow layer allows the deep cold of the Arctic winter to penetrate more deeply into the ground, maintaining the permafrost temperature. Without large grazers, the fluffy insulating snow acts as a blanket over the permafrost, trapping heat from the relatively warmer autumn soil temperature and slowing the freeze. The logic is intriguing. Whether a reintroduced mammoth-like creature, engineered from modified elephant genetics and born in a laboratory, could realistically restore the ecological function of the mammoth across the vast Pleistocene steppe of the Canadian and Siberian Arctic is another question entirely. The scale of the territory involved, the complexity of the ecosystem interactions, and the practical challenges of breeding and managing a herd of genuinely new creatures in one of the most remote and extreme environments on Earth make the project more visionary than operational. But the underlying research about how megafaunal grazing affected permafrost temperatures in the Pleistocene and how its loss might be implicated in the permafrost instability we are now seeing is scientifically legitimate and has influenced the broader discussion of permafrost management. The concept of permafrost management itself, the idea that it might be possible not merely to observe and document the thaw, but to actively intervene to slow or reverse it, is gaining traction in discussions that until recently would have seemed to belong to science fiction. Beyond the megafaunal restoration concept, researchers have proposed other interventions, including the application of light-colored, reflective materials to the tundra surface to increase its albedo, the injection of freezing brine into permafrost to artificially maintain its temperature, and the installation of heat pipes that would accelerate the freezing of permafrost during winter to compensate for the summer warming. All of these ideas face enormous challenges of scale, cost, and ecological impact. None of them is currently operational at any significant scale, but the fact that they are being seriously discussed is an indication of how seriously the scientific community is beginning to treat the permafrost situation as a crisis that may require active intervention rather than passive adaptation. The history of Canadian Arctic exploration is a history of encounters with the permafrost, even when the explorers did not have a word for it or an understanding of what they were experiencing. The European expeditions that probed the Canadian Arctic from the 16th century onward were consistently confounded by the ground conditions they encountered. Ground that was solid in winter became treacherous in summer. Water pooled in unexpected places. Digging was impossible in some areas and unpredictably easy in others. The landscape that the explorers were trying to cross was a landscape shaped by permafrost in ways that they did not understand, and that they interpreted instead through the cultural and religious frameworks they had brought with them from Europe. The Franklin expedition's catastrophic failure in 1845 to 1848 was not caused by permafrost, but the expedition's story is entangled with the physical environment of the high Arctic in ways that the permafrost has helped preserve for our examination. The ships HMS Erebus and HMS Terror, which were abandoned in the ice in April 1848 and which carried the records and equipment of the expedition, sank in the waters of the Northwest Passage and lay on the seabed for more than 160 years before being found by Canadian researchers in 2014 and 2016 respectively. The cold, dark conditions of the seabed preserved the wrecks in remarkable condition, in the same way that the permafrost has preserved the biological specimens of the Pleistocene. The Erebus and Terror, like Nunchoga, are examples of the preserving power of cold that characterizes the Canadian North. The ships were found in waters that are becoming more navigable as the sea ice retreats. The opening of the Northwest Passage, the sea route through the Canadian Arctic that Franklin died trying to find, is now becoming a reality not because of human navigation achievement, but because of climate change. The Arctic Ocean ice that blocked the passage for all but the most ice-capable ships for most of the year is now retreating sufficiently in summer to allow transit by ordinary commercial vessels. This development, which would have seemed miraculous to Franklin and every Arctic explorer before him, is being greeted with a mixture of commercial anticipation and environmental alarm by the Canada of the 21st century. The Indigenous peoples of Canada's north, whose ancestors watched the Franklin ships sail into the ice, and whose oral traditions preserved accounts of the expedition's men abandoning their ships and walking south across the ice, have a perspective on the opening of the Northwest Passage that is shaped by a relationship with the land and sea ice that extends back far beyond any European presence. The knowledge that the Inuit have accumulated about the conditions of the Canadian Arctic, including which waters are navigable in which conditions and which ice is safe to travel on, is now being sought by shipping companies and government regulators who recognize that this knowledge, accumulated over thousands of years, may be more valuable than any satellite data for understanding the real-time conditions of a changing Arctic. What is happening beneath Canada is not simply a scientific phenomenon. It is a convergence of geological time and human time, of ancient biology and modern consequence, of indigenous knowledge and international science, of historical record and future risk. The permafrost that is thawing has been frozen since before modern human civilization began. The world it is revealing, specimen by specimen, layer by layer, is a world that no human memory reaches. And the world it is creating as it thaws, the landscape of thermokarst lakes and tilted buildings and methane seeps and exposed ancient DNA, is a world that no one predicted and no one is fully prepared to navigate. The specimens that are coming out of Canada's permafrost are each a kind of message in a bottle from the deep past. The baby mammoth Nunchoga, with her fur still intact and her trunk still flexible, is a message from the Pleistocene, 35,000 years old, telling us that an entire world of great creatures lived and breathed and moved across this land. The ancient horse with its intact genome is a message about the deep evolutionary history of a species that went extinct in North America and was brought back by Spanish colonizers thousands of years later, closing a loop of biological history across the Pacific. The ancient viruses that can be coaxed back into replication in a laboratory dish are messages from a microbial world that predates every human civilization and that has survived sealed in ice through every century of human history. The question of what those messages mean, what we should do with them, how we should respond to the knowledge that the permafrost is opening and its contents are joining the living world again, is not a question that science alone can answer. It is a question for Canada and for every society that is connected to the circumpolar north and to the global climate system that is driving the thaw. It is a question about what kind of past we are willing to inherit and what kind of future we are willing to accept. The permafrost of Canada has been waiting for this moment for longer than anyone can comprehend. The thaw has begun. The contents are emerging, and among everything that is coming out, some of it is beautiful, some of it is scientifically invaluable, and some of it, by the best available evidence, should not be in contact with the living world at all. The challenge is distinguishing between the three and responding with the appropriate combination of wonder, caution, and urgency before the opportunity to do so is lost. In the end, what Canada's permafrost reveals is not only the deep history of a land, but the consequence of treating that land as if its systems were static, permanent, and endlessly resilient. The word permafrost itself, permanent frost, encodes the assumption that this frozen ground would always be there, that it was a fixed feature of the northern landscape as reliable and unchanging as the bedrock beneath it. That assumption was wrong. The permanence was borrowed. It was a condition created by specific climatic circumstances maintained over tens of thousands of years and now being dismantled by a different set of climatic circumstances created in a geological instant by the industrial activities of a single species. The history of Canada cannot be fully understood without understanding the permafrost. It shaped the landscape that Indigenous peoples navigated for thousands of years before European contact. It shaped the conditions that European explorers encountered and that defeated so many of them. It preserved the evidence of the natural world that existed before the last great extinction, the one that wiped out the megafauna of Beringia at the end of the Pleistocene in a cascade of climate change and human hunting pressure that resonates uncomfortably with the present moment. It preserved the bodies of the men who sailed with Franklin and died in the Arctic, looking for a passage that is now opening because the ice that stopped them is melting. The permafrost is a library. The library is on fire, and what is flying out of the flames is history that we did not know we had, knowledge that we are not prepared to receive, and risks that we are only beginning to understand. The story of Canada's permafrost is not a story with a simple ending. It is a story that is being written now, in frozen ground and melting ice, in ancient DNA and reactivating microbes, in tilting buildings and draining lakes, in the testimony of Indigenous elders and the data of satellite sensors. Whatever comes next, we should be paying attention, because the permafrost, which has been silent for longer than any of us can imagine, has finally started to speak. And what it is saying will change everything we thought we knew about this land, this country, and this planet. The question is not whether we are willing to listen. The question is whether we are willing to act on what we hear before it is too late to make any difference at all. The specific regions of Canada where permafrost thaw is most visibly and urgently underway each carry their own particular character, their own history, and their own version of what the thaw means for the people who live there. The Yukon, which has produced the most spectacular biological specimens and which hosts the most active placer mining industry in the country's permafrost zone, is perhaps the most familiar of these regions to the wider Canadian public. But the Northwest Territories, Nunavut, northern British Columbia, northern Manitoba, and the Hudson Bay lowlands each present their own permafrost stories, and together they form a picture of change that spans the full breadth of the country from the Pacific coast to the Atlantic. The Hudson Bay lowlands represent one of the least discussed but most scientifically significant permafrost regions in Canada, stretching across the southern edge of the Hudson Bay and encompassing large portions of northern Ontario and Manitoba. The Hudson Bay lowlands constitute the largest peatland complex in North America and one of the largest in the world. The peatlands of this region are built on permafrost that has allowed organic material to accumulate over thousands of years without decomposing, creating deposits of peat in some areas many meters deep. The carbon stored in the Hudson Bay peatlands alone represents a quantity of greenhouse gas potential that dwarfs many of the better-known carbon stores of the global north. The peat itself is ancient. In the deepest layers, it was laid down by the plants of the early Holocene, the period immediately following the retreat of the great glaciers, when the land surface rebounded from the crushing weight of the ice sheets and the first communities of pioneer plants colonized the newly exposed ground. Those plants died, fell into the waterlogged substrate, and because the cold and the waterlogging prevented decomposition, they accumulated rather than rotting away. Layer by layer, century by century, the peat built up, creating a landscape that looks solid from the surface, but that is, in reality, a vast sponge of compressed organic material, waterlogged and underlain by permafrost, maintaining a precise balance between cold preservation and slow biological accumulation that has persisted for approximately 8,000 years. That balance is now being disrupted. Warming temperatures and changes in precipitation patterns are altering the hydrology of the Hudson Bay peatlands in ways that are shifting the equilibrium between carbon accumulation and carbon release. Areas that were previously net carbon sinks, absorbing more carbon through plant growth than they release through decomposition, are becoming net carbon sources as the warming promotes the decomposition of previously frozen organic material. The transition from sink to source is not uniform across the landscape, but it is widespread enough to be detectable in atmospheric measurements of methane and carbon dioxide over the Hudson Bay region. The thermokarst processes that are transforming the surface of the Hudson Bay peatlands are particularly dramatic in a feature called thermokarst bogs, or collapse scars. When a layer of permafrost that contains a high proportion of ice melts, the ice volume is lost, and the ground surface above it collapses, creating a water-filled depression. In the peatland context, these collapse scars fill with water and become ponds that are open to the atmosphere, where methane produced by the decomposition of the surrounding peat can bubble up through the water and escape directly into the air. The collapse scars in the Hudson Bay peatlands have been growing in number and extent over the past several decades, visible in aerial and satellite photography as dark water-filled holes spreading through the light-colored peat surface. The birds that depend on the Hudson Bay peatlands, including vast numbers of migratory waterfowl and shorebirds that breed in this region every summer, are already responding to the changes in the landscape. The timing of migration, the selection of breeding sites, and the availability of food resources are all being affected by the shift in the hydrology and vegetation of the peatlands. Some species that are adapted to the wet, peat-based environment are benefiting from the increase in open water. Others, including species that depend on the dry or moist peat surface for nesting, are being displaced by the expanding thermokarst ponds. The net effect on the ecology of this region, which is one of the most important bird breeding areas in North America, will unfold over decades in ways that are difficult to fully predict but easy to recognize as significant. Northern Ontario's relationship with permafrost is less dramatic, but no less real. The sporadic and discontinuous permafrost that underlies the boreal forest of northern Ontario is not the deep, ancient permafrost of the high Arctic. It is relatively shallow, relatively warm, and relatively recent in geological terms. It formed primarily during the Little Ice Age, the period of enhanced cold that lasted approximately from the 14th to the 19th century, and it has been marginal in thermal terms since the end of that cooler period. This means that the permafrost of northern Ontario is among the most sensitive to warming of any permafrost in Canada. Small increases in temperature push it past the threshold of stability. The permafrost that exists there today may be largely gone within decades. The consequences for the boreal forest are already visible. Permafrost, even where it is patchy and shallow, provides a cold, stable soil layer that influences drainage, vegetation, and tree root depth. Where it thaws, the soil conditions change. Trees that were stable in frozen ground suddenly find their root systems in mobile, waterlogged substrate, and the patterns of forest composition and structure shift accordingly. The drunken forest phenomenon is appearing in areas of northern Ontario that have not previously experienced visible permafrost-related ground movement, evidence that the thaw is penetrating into the margin zones where permafrost has been present but not obvious. The geology of the Canadian Shield, which underlies much of northern Canada's permafrost zone, adds a complicating factor to the story of permafrost change. The Shield is ancient, hard bedrock, and in most places it is not itself frozen. The permafrost sits in the unconsolidated material above the bedrock, in the glacial sediments, organic soils, and transported materials that have accumulated on the Shield surface since the last glaciation. This means that the permafrost is relatively thin in many areas and sits on a foundation that does not freeze. When the permafrost thaws from above due to warming air temperatures, there is no deeper frozen reservoir to replace it. The thaw, once it has gone through the shallow layer of permafrost, reaches unfrozen bedrock and stops. The permafrost, once lost, is gone. The Canadian Arctic archipelago, the vast chain of islands stretching from the northern tip of Hudson Bay to Ellesmere Island at the extreme northern end of the country, holds some of the oldest and deepest permafrost in Canada. The permafrost beneath the larger islands of the archipelago can reach depths of several hundred meters in some locations. This deep permafrost contains the coldest and most stable section of Canada's frozen ground, farthest from the surface where warming air temperatures first make contact with the land. It is also, for that reason, the section of Canadian permafrost that has received less attention from researchers whose instruments and funding have been focused on the more accessible and more rapidly changing southern margins. But the high Arctic is warming. The temperature trends at the weather stations on the islands of the Canadian Arctic archipelago, while representing a shorter record than what exists for more southerly locations, show warming rates that are among the highest in the world. The islands that host the thickest and oldest permafrost in Canada are the same islands that are experiencing the most dramatic air temperature increases. The deep permafrost will not respond to these temperature changes as quickly as the shallow permafrost further south, because it takes time for surface temperature changes to penetrate to depth. But the changes that are happening at the surface now will eventually make their way downward, and when they do, the consequences for the deep permafrost of the high Arctic will be measured not in decades, but in centuries. The research expeditions that venture into the Canadian high Arctic to study its permafrost and its preserved biological content operate in conditions that are themselves a reminder of how extreme this environment is. Scientists working in Nunavut or on Ellesmere Island during the brief summer research season, face temperatures that, even in the warmest months, can drop below freezing without warning. Equipment fails. Helicopters are grounded by sudden weather. The logistics of supplying a research camp hundreds of kilometers from any road or settlement require careful planning and reliable air support. The window of opportunity for outdoor research is measured in weeks rather than months, and the scientific work that must be compressed into that window reflects the urgency and intensity of working at the edges of what is humanly possible. Despite these challenges, the body of knowledge that has been accumulated through decades of Arctic research expeditions is remarkable. The sediment cores drilled from Arctic lakes and bogs carry records of climate change, going back thousands of years in the biological and chemical evidence preserved in their layers. The ice cores drilled from Arctic glaciers and ice caps carry records going back hundreds of thousands of years in the gas bubbles and dust particles trapped in their ice. The permafrost cores drilled by geologists and geocryologists carry records of ground temperature going back as far as the instruments and the frozen sediment can take them. Together, these records paint a picture of an Arctic environment that has been through dramatic changes before, and that is now entering a period of change that, in its rapidity, if not its magnitude, is unprecedented in the geological record. One of the most specifically unsettling aspects of what is emerging from Canada's permafrost is the documented case of ancient influenza. In 1997, a team of researchers led by Johan Holten traveled to the remote Alaskan village of Brevig Mission, where in 1918, the influenza pandemic killed approximately 72 of the village's 80 residents in just 5 days. The bodies of the victims had been buried in the permafrost, and Holten, who had visited the site previously in 1951 in an unsuccessful attempt to recover viable viral material, returned with the new genetic tools of the late 1990s and succeeded. From the lung tissue of a woman who had been preserved in the frozen ground for 79 years, he extracted fragments of the influenza A virus that had killed her, fragments sufficient for the teams of virologists who subsequently analyzed them to reconstruct the entire genome of the 1918 influenza strain. The 1918 influenza, the strain responsible for one of the deadliest pandemics in human history, killing between 50 and 100 million people worldwide, was for decades a scientific mystery. Samples of the virus collected from living patients during the pandemic had not been preserved in any way that allowed genetic analysis. The Brevig mission recovery was the key that unlocked the genome of this historical pathogen and allowed researchers to understand for the first time what made the 1918 flu so deadly and why it affected young healthy adults far more severely than most influenza strains. The research that followed the genome reconstruction was invaluable for pandemic preparedness. Understanding the specific genetic features that made the 1918 flu pandemic capable has informed the design of surveillance systems, vaccine development strategies, and pandemic response protocols. In a very real sense, the permafrost of Alaska preserved not just the body of one woman, but the scientific key to understanding the deadliest pandemic of the modern era. The same could be true for other pathogens preserved in Canadian permafrost. The scientific knowledge locked in those ancient microbes is not only dangerous, it is also potentially illuminating, potentially therapeutic, potentially the key to understanding diseases that continue to affect the modern world. Brevig Mission's case is Alaskan, but the permafrost that preserved those victims is continuous with the permafrost of the Yukon. The same type of frozen ground that held the 1918 flu for nearly a century extends across the Alaska-Yukon border in an unbroken sheet. Communities in northern Canada experienced the 1918 pandemic with devastating intensity, particularly Indigenous communities that had no prior exposure to influenza and no immunity to protect them. The victims of those communities were buried, in many cases, in the same permafrost that holds the Pleistocene specimens. Whether the influenza strains that killed Canadian Indigenous communities in 1918 are preserved in the permafrost where their victims were buried, and whether those strains might be accessible through the same methods that were applied at Brevig Mission are questions that have not been fully addressed. The revival of ancient plant life from permafrost seeds and tissue represents a gentler face of the same phenomenon that makes ancient viruses alarming. In 2012, a team of Russian researchers announced that they had successfully grown plants from the tissue of Silene stenophila, a narrow-leafed campion that had been buried in permafrost by squirrels approximately 32,000 years ago. The fruit and seed material recovered from the ancient squirrel caches was viable enough to produce flowering plants when cultured in laboratory conditions. The plants that grew were fertile and genetically similar to modern populations of the same species, but with some differences in flower morphology that reflected the long period of isolation in the permafrost. The revival of 32,000-year-old plants from permafrost tissue is not an isolated stunt. It is a demonstration of a principle that has profound implications for conservation, biology, paleobotany, and the understanding of how life persists through extreme conditions. If plant tissue can remain viable for 32,000 years in permafrost, what are the limits of biological preservation in frozen ground? The discovery has driven renewed interest in the permafrost as a repository of ancient genetic material and in the possibility that it contains biological resources that could be valuable for modern agriculture, medicine, and ecosystem restoration. The practical implications extend to the possibility of recovering plant material from species that went extinct at the end of the Pleistocene, species that coexisted with the mammoths and the ancient horses and the cave lions, and that disappeared when the steppe tundra ecosystem of Beringia collapsed. These extinct plants, which may have had properties that made them particularly well adapted to cold, nutrient-poor conditions, could theoretically be revived or have their genetic characteristics incorporated into modern plant breeding programs. The permafrost, in this vision, is not only a library, but a seed bank, a repository of genetic diversity that long predates any human agricultural system and that contains varieties and traits that modern breeding has not imagined. The Canadian government's scientific and regulatory response to the permafrost situation has evolved significantly over the past 2 decades, though it has consistently lagged behind both the pace of change and the scale of the challenge. The 2021 National Adaptation Strategy, which for the first time established a comprehensive federal framework for responding to climate change impacts in Canada, includes permafrost as one of the priority areas requiring coordinated national action. The strategy acknowledges the infrastructure consequences of permafrost thaw, the ecological consequences for northern biodiversity, and the consequences for northern and Indigenous communities, while falling short of the specific programmatic commitments and funding levels that advocates for northern Canada have called for. The Indigenous-led governance initiatives that have emerged in Canada's north over the past several decades are becoming increasingly important as the primary vehicle for making decisions about the North's changing landscape. The devolution of territorial governance in the Yukon and the Northwest Territories, and the creation of the territory of Nunavut in 1999, have transferred significant authority over land management decisions to governments that are more directly responsive to northern communities and more likely to incorporate Indigenous knowledge and values into their decision-making. The management of permafrost-related issues, including the disposition of paleontological specimens discovered on Indigenous territories, the design of monitoring systems that incorporate traditional ecological knowledge, and the allocation of resources for infrastructure adaptation in northern communities is increasingly happening within governance structures that reflect the demographic reality of Canada's north, where Indigenous peoples are the majority population. The Saatu, Dene, and Métis communities of the Northwest Territories, whose traditional territory spans some of the most permafrost-affected lands in the country, have been working to document the changes in their landscape through both scientific monitoring and traditional knowledge recording. The community-based monitoring programs that have been developed in partnership with federal and territorial agencies allow community members, including hunters, fishers, and harvesters, whose activities take them across the land in all seasons, to record and report observations about landscape changes, wildlife behavior changes, and unusual findings including permafrost specimens. This distributed monitoring, carried out by people with intimate and long-standing knowledge of specific places and their normal conditions, provides a level of spatial and temporal coverage that formal scientific monitoring programs cannot match. The Deschaux First Nations, whose territory covers much of the Mackenzie Valley and the area around Nahanni National Park Reserve in the Northwest Territories, have been particularly active in asserting their rights and responsibilities in relation to the biological and paleontological resources of their territory. The Mackenzie Valley, which follows one of Canada's great rivers from its origins near Great Slave Lake to the Beaufort Sea, is a corridor of diverse ecosystems that includes some of the most productive permafrost-influenced landscapes in the country. The changes that are happening in the Mackenzie Valley, including the expansion of shrub vegetation into areas that were formerly tundra, the drying of wetlands in some areas while new ponds form in others, and the emergence of previously frozen organic material from eroding riverbanks, are being observed and documented by Deschaux community members who travel these landscapes regularly. The Mackenzie River itself plays a significant role in the permafrost story. As the largest river system in Canada's north, it drains an enormous catchment that includes vast areas of thawing permafrost. The carbon and nutrients released from thawing permafrost are carried by the Mackenzie and its tributaries to the Beaufort Sea, where they affect the chemistry and biology of the coastal ocean. The browning of northern rivers and lakes, a phenomenon observed across the circumpolar north, where thawing permafrost is releasing dissolved organic carbon into waterways, is altering the light environment of these water bodies in ways that affect phytoplankton growth, fish habitat, and the broader aquatic ecosystem. The Mackenzie's discharge of permafrost-derived carbon to the Beaufort Sea represents a connection between what is happening beneath the ground and what is happening in the ocean that scientists are only beginning to quantify. The geophysical relationship between permafrost and sea level is another connection that receives insufficient attention in public discussions of permafrost change. The ice that is stored in permafrost is not glacier ice. It is not counted among the sources of sea level rise that most people think of when they hear about ice melting. But the relationship runs in the other direction. Rising seas are themselves a driver of coastal permafrost thaw. The coastlines of northern Canada are among the most rapidly eroding in the world, as the combination of reduced sea ice that previously buffered the coast from wave action and the thawing of the coastal permafrost that had held the coastal cliffs together has produced erosion rates that in some places reach tens of meters per year. Communities that were built on what appeared to be solid, permanent coastal ground are losing significant portions of their territory to the sea every decade. The community of Tuktoyaktuk on the Mackenzie Delta in the Northwest Territories has been particularly affected by this coastal erosion. Tuktoyaktuk sits on a peninsula of permafrost that is being undercut by the warming and increasingly ice-free Beaufort Sea. Houses that were safely distant from the waterline a generation ago are now at the edge of actively eroding banks. The community has invested in shoreline protection measures, including riprap and seawalls, but the scale of erosion is testing the limits of what engineering can achieve against the combination of rising sea temperatures, declining sea ice, and thawing permafrost that is making the coastline progressively less stable. The longer-term question of whether Tuktoyaktuk and other similarly situated communities will need to relocate is one that no government has been willing to address with the decisiveness and resources that a serious relocation program would require. The International Permafrost Association, the scientific body that coordinates permafrost research globally, maintains a network of monitoring sites across the circumpolar north through the Global Terrestrial Network for Permafrost. Canada contributes significantly to this network through the monitoring sites operated by federal and provincial agencies and universities. The data from this network shows clearly that the warming trend in permafrost temperatures is consistent, widespread, and accelerating. The most recent synthesis of network data covering the period from 2007 to 2019 found that permafrost temperatures increased at most monitoring sites, with the largest increases occurring in the coldest permafrost regions of the high Arctic, a finding that is particularly concerning because the coldest permafrost contains the most ancient material and the deepest stores of frozen organic carbon. The connection between permafrost research and the broader debate about climate change in Canada has sometimes been uncomfortable. The fossil fuel industry, which is one of the most powerful economic and political forces in Canada, has interests that are directly affected by both the permafrost situation and the climate policies that would address the underlying warming. The oil sands of northern Alberta are located at the southern edge of the discontinuous permafrost zone, and the extraction operations there both rest on permafrost and contribute to the warming that is thawing it. The pipelines that carry oil and gas from the north to the south cross extensive areas of permafrost and are affected by its thaw in ways that require continuous engineering adaptation. These connections create a political and economic context for permafrost science in Canada that is different from what exists in countries without comparable fossil fuel industries. The scientists who study permafrost and document its thaw are, in effect, documenting the consequences of an industry that is central to the Canadian economy. The findings of permafrost science are not politically neutral. They are evidence in a policy debate about energy production, greenhouse gas emissions, and the pace and ambition of Canada's climate response. This does not invalidate the science, but it does mean that the science operates in a context where its implications are contested and where the institutions that fund research, regulate industry, and make policy are navigating real conflicts of interest. The global scientific community that studies permafrost includes researchers from Canada, Russia, the United States, Scandinavia, China, and many other countries, all working on what is ultimately a shared problem. The permafrost that is thawing in Canada is connected to the permafrost that is thawing in Russia, which is connected to the climate system that is warming everywhere, which is driven by greenhouse gas emissions from every country in the world. The national boundaries that divide the permafrost zone of the circumpolar north are political constructs superimposed on a geological reality that knows nothing of borders. The carbon that is released from Canadian permafrost mixes in the same atmosphere as the carbon released from Siberian permafrost and from the tailpipes of vehicles and the smokestacks of power plants on every continent. The future of Canada's permafrost, under the various climate scenarios that scientists have modeled, ranges from severe to catastrophic, depending on how rapidly global greenhouse gas emissions are reduced. Under the highest emission scenarios, in which current trends in fossil fuel use continue without significant mitigation, the models project that the continuous permafrost zone of Canada's north will retreat significantly northward by the end of this century, with widespread thaw of the existing permafrost zone and the release of enormous quantities of carbon that would further accelerate warming in a self-reinforcing loop. Under the most optimistic emission scenarios, in which global emissions are rapidly and dramatically reduced, the permafrost continues to thaw, but at a slower rate that would preserve more of its extent and give the ecosystems and communities of the north more time to adapt. The window for making decisions that would influence which of these scenarios is realized is closing. The carbon that has already been emitted has already committed the world to a certain degree of warming and a certain amount of permafrost thaw, regardless of what happens next. The decisions made in the next decade will determine whether the thaw remains within ranges that, while severe, are manageable, or whether it enters the territory of self-reinforcing feedback loops that take it beyond any human ability to influence. Canada's contribution to these global decisions is constrained by its size and its emissions profile, but it is not negligible. A country that is simultaneously one of the world's major greenhouse gas emitters per capita and one of the most directly affected by permafrost thaw has a particular responsibility to take both the cause and the consequences seriously. The discovery of ancient life in the permafrost, whether it is the intact body of a baby mammoth or the viable genome of an ancient virus, challenges the assumption that the past is truly past, that what is gone, and that the world before human civilization is accessible only through the fragmentary and indirect evidence of conventional fossils and archaeological sites. The permafrost of Canada is a place where the boundary between past and present is genuinely permeable, where organisms that lived tens of thousands of years ago can be recovered, studied, and in some cases reactivated as participants in the living world. This permeability is simultaneously thrilling, scientifically invaluable, and genuinely alarming. The ethical frameworks that human societies have developed for dealing with the past, the protocols of archaeology and paleontology, the laws governing cultural property, the traditions of Indigenous stewardship, the conventions of scientific research, were not designed for a situation in which the past is literally melting into the present. They were designed for a world in which ancient remains were fixed in place, recoverable only through careful and deliberate excavation, and safely dead in the sense that they could not affect the living world through anything other than the knowledge they generated. The ancient viruses that can be revived from permafrost do not fit into that framework. They are not simply historical artifacts. They are potentially active biological agents, and the protocols for managing them require a different kind of thinking from anything that the study of the ancient world has previously required. The intersection of climate change, ancient biology, Indigenous rights, national sovereignty, and global governance that is represented by the situation of Canada's permafrost is one of the most complex policy challenges of the contemporary world. There is no existing institution or framework that is adequate to address all of its dimensions simultaneously. The international agreements on climate change provide a framework for addressing the underlying cause of permafrost thaw, but they are not being implemented at a speed or scale that would prevent the most serious consequences. The national and territorial governments of Canada provide frameworks for managing the immediate consequences of thaw on infrastructure and communities, but they lack the resources and the jurisdictional coherence to do so comprehensively. The scientific community provides knowledge and analysis, but it cannot by itself translate that knowledge into the political and economic decisions that would matter. What is needed, and what is only partially present, is a recognition that the permafrost situation is not a sectoral problem amenable to sectoral solutions. It is not only a climate problem, or only an infrastructure problem, or only a biodiversity problem, or only an indigenous rights problem. It is all of these simultaneously, and addressing it requires the kind of integrated, cross-sectoral thinking and action that is the most difficult thing for any governance system to produce. The fact that Canada has begun to develop some of the institutional and political frameworks for this kind of thinking through Indigenous co-management agreements, through integrated northern development policies, through the work of the Polar Knowledge Canada Agency and its research programs, is a reason for qualified optimism. The fact that these frameworks are still far from adequate to the scale and urgency of what is happening is a reason for serious concern. The baby mammoth Nun Cho Ga, lying in a glass case in a Whitehorse museum, is perhaps the most powerful symbol of all of this. She is 35,000 years old. She is extraordinarily beautiful. She is a creature from a world that no human being has ever seen and that we are only beginning to understand. She was preserved by the same permafrost that is now thawing under the warming of the contemporary atmosphere, the atmosphere that has been altered by the industrial civilization that stands gazing at her through the museum glass. She is, in a sense, a messenger from the Ice Age to the age of industrial capitalism, delivered by the very processes of planetary change that capitalism has set in motion. She could not have been preserved this well if the permafrost had been anything but what it was, ancient, stable, and cold, and she may be one of the last specimens of her kind to emerge from the Canadian permafrost in this condition, before the thaw progresses to the point where the remaining frozen specimens begin to degrade before they can be found. The same warming that brought her to the surface may eventually destroy what remains in the ground before anyone can recover it. She is both a gift and a warning, and the two cannot be separated. What is happening in Canada's permafrost is, at its deepest level, a story about time, about the vast spans of geological time that have made this land what it is, the millions of years of continental drift and mountain building, the hundreds of thousands of years of ice ages and interglacials, the tens of thousands of years of the Pleistocene world that is now emerging from the ground, and the few hundred years of industrial human activity that is now unlocking all of that frozen time and releasing its contents into the present. The permafrost was a boundary between past and present, a wall of ice and frozen soil that kept the deep history of this land contained and separated from the living world above it. That wall is coming down, and what is on the other side of it is something that the world, and Canada in particular, is only beginning to comprehend. The scientists who study permafrost for a living occupy a peculiar professional position. They are experts in something that most people never think about and that most governments treat as a secondary consideration, yet they carry knowledge that may be among the most consequential in contemporary science. When a permafrost researcher presents findings at an international conference showing that the ground temperatures at a monitoring station in the Northwest Territories have risen by 1.3 degrees Celsius over the past 15 years, the response from the small community of specialists in the room is one of deep concern. The response from the rest of the world is, by and large, silence. This gap between what the specialists know and what the public understands is not unique to permafrost science, but it is particularly stark in this case because the consequences of the knowledge are so direct and so large. The permafrost is not a theoretical system that might possibly affect something in the distant future under certain conditions. It is a physical reality present beneath half of Canada's land area right now, changing in measurable ways right now, releasing biological and chemical contents into the environment right now, and affecting the lives of tens of thousands of Canadians in the North right now. The gap between the urgency of the scientific community's concern and the passivity of the political and public response is, in its own way, as alarming as the permafrost situation itself. Part of the challenge is the nature of the change. Permafrost thaw is not a single dramatic event. It is a gradual process happening across an enormous area in ways that are visible only if you know what you are looking for, or if you are one of the people whose home is tilting, or whose trail has become impassable. The dramatic discoveries, the baby mammoth, the ancient virus, the methane crater, are the moments when the permafrost story becomes briefly visible to a wider public. But between those moments, the slow, relentless, cumulatively enormous transformation continues without attracting attention. The research stations that maintain continuous monitoring of Canadian permafrost are among the most important scientific infrastructure in the country, and they are chronically underfunded relative to their importance. The stations at places like Eureka on Ellesmere Island, at Resolute Bay in Nunavut, and at the various monitoring sites across the Yukon and the Northwest Territories maintain temperature records, measure gas flux, document ground movement, and collect the specimens and samples that form the physical evidence base for everything else that permafrost science produces. The scientists who staff these stations, often in conditions of considerable physical hardship and professional isolation, are performing a public service that is vastly undervalued by the institutions that nominally support them. The broader infrastructure of Canadian Arctic science, which includes not only the permafrost monitoring network, but also ocean observing systems, atmospheric monitoring stations, wildlife survey programs, and Indigenous-led community monitoring initiatives, represents a distributed system for understanding one of the most rapidly changing environments on Earth. This system is vulnerable to budget cuts, to the loss of institutional memory when experienced researchers retire, to the failure of aging monitoring equipment in remote locations, and to the political winds that shift federal science priorities from decade to decade. The value of long-term monitoring data, which lies precisely in its long-term continuity, is poorly served by funding structures that operate on annual or biennial cycles and that can be disrupted by changes in government priorities. The students and early career researchers who are entering permafrost science today are doing so with a full awareness that they are studying something that is changing in real time and that their research has implications far beyond the academic. The graduate students who are analyzing ancient DNA extracted from permafrost specimens, who are modeling the carbon release from thawing peatlands, who are documenting the subsidence of northern infrastructure, and who are working with Indigenous communities to document traditional ecological knowledge, are the scientists who will be leading this field when the consequences of today's permafrost thaw become fully apparent in the decades to come. The training they receive, the research infrastructure they have access to, and the institutional support that sustains their work are investments whose return will be measured in the quality of Canada's response to one of the most significant environmental challenges in its history. The educational dimension of the permafrost story is itself significant. Most Canadians learn very little about the geography and ecology of their own north. The school curricula of the southern provinces, where most Canadians live, treat the North as a remote and exotic region rather than as an integral part of the national territory, whose changes are relevant to every citizen. The story of permafrost, of what it is, what it contains, and what is happening to it, is a story that should be part of every Canadian's basic geographic and environmental literacy. It is as much a part of the Canadian story as the Rocky Mountains, or the Great Lakes, or the St. Lawrence River, and its transformation is as significant to the future of the country as any other environmental change underway. The relationship between Canada's permafrost and the broader global discussion of climate change and biodiversity loss is sometimes lost in the fragmentation of environmental discourse into separate topics, separate advocacy communities, and separate policy conversations. The thawing of the permafrost is at once a consequence of climate change, a driver of further climate change, a threat to biodiversity, a source of extraordinary paleontological discovery, a public health concern, an infrastructure challenge, an Indigenous rights issue, and a question of global governance. The people and institutions working on these different dimensions of the permafrost situation are not always in communication with each other, and the synthesis that would allow the full picture to be understood and acted upon is still incomplete. What the permafrost of Canada ultimately represents in its totality is the accumulated consequence of geological time meeting the accelerated consequence of human industrial time. The tens of thousands of years of biological preservation that the permafrost has performed, patiently and silently beneath the land that became Canada, are now being undone in a geological instant. The library that the earth assembled over millennia is being opened, not in the measured and deliberate way of a scholarly archive, but in the chaotic and uncontrolled way of a building whose walls are collapsing. The contents are spilling out faster than they can be cataloged, studied, or safely managed. Some of what is spilling out is treasure, some of it is history, and some of it may be danger that we have not yet learned to recognize. The story of Canada's permafrost is not finished. It has barely begun in terms of what the thaw will ultimately reveal and release. The decisions that are made in the next decade, the decade of the 2020s, will determine how much of this story is characterized by knowledge, caution, and adaptation, and how much is characterized by loss, surprise, and consequences that arrive faster than any response can be prepared. The frozen ground of Canada's north has been patient for a very long time. The time for patience on the part of those who must respond to what it is releasing is running out. Whatever lies ahead, one thing is certain. The permafrost of Canada is no longer silent. It is speaking in the language of thawing ground and emerging specimens, of rising methane and reviving microbes, of cracking buildings and draining lakes, of ancient DNA and prehistoric fur. And the message it is sending, encoded in all of these different voices speaking simultaneously across half a continent, is one that requires the full attention of everyone who lives in this country, everyone who depends on this planet's climate system, and everyone who believes that the past and the future of this land deserve to be taken seriously. The time to listen is now. The time to act on what we hear is also now. The two are not separate moments. They are the same moment, and it is the moment we are living in. The specific and human stories embedded within the larger scientific narrative of permafrost thaw deserve more attention than the broad sweep of geological and climatological data typically receives in discussions of this topic. When researchers at the University of Calgary published findings in 2021 showing that the permafrost beneath parts of Yellowknife, the capital of the Northwest Territories, had warmed by nearly 2 degrees Celsius in the previous 2 decades, the story they were telling was not abstract. Yellowknife is a city of approximately 20,000 people. It has hospitals, schools, government buildings, and ordinary homes, many of them built on ground that is now behaving differently from the way it behaved when they were constructed. The engineers and municipal officials who must decide how to maintain and adapt this infrastructure are making decisions under genuine uncertainty about how quickly and how dramatically the ground beneath them will continue to change. The mental health consequences of living in a landscape that is visibly and rapidly changing around you have been documented in qualitative research conducted with northern Indigenous communities, but have received insufficient systematic attention. The concept of solastalgia, the sense of grief and distress associated with environmental change in one's home environment, was developed by philosopher Glenn Albrecht specifically to describe the emotional experience of people whose home landscapes change in ways they find distressing and over which they have no control. The people of Canada's thawing permafrost north are experiencing solastalgia on a scale that no community in the temperate south can fully appreciate. The landscape that their grandparents navigated, that their parents depended on, and that they themselves have built their lives around is becoming something else, something unfamiliar, something that in some places and in some ways is no longer safe to trust. The water systems of northern Canada are among the most directly and severely affected by permafrost thaw. The lakes and rivers of the permafrost zone depend on the frozen ground in ways that most people who live near southern Canadian lakes and rivers do not appreciate. The permafrost acts as an impermeable layer that prevents water from draining downward through the soil. When it thaws, the hydrology of entire watersheds changes. Some lakes, their permafrost dams dissolved, drain catastrophically, and become meadows. Others expand as thermokarst processes collapse more land into them. Rivers shift channels, pick up enormous loads of sediment from the eroding permafrost, and change color from clear to brown as dissolved organic carbon floods in from the thawing soils. The drinking water security of northern communities is directly tied to these hydrological changes. Communities that have relied on specific lakes or rivers for generations are finding that those water sources are changing in ways that affect both quantity and quality. The turbidity of northern rivers and lakes is increasing as permafrost erosion delivers sediment and dissolved organic material. Treatment infrastructure that was designed for the water quality of a previous era may be inadequate for the water quality of the present. The cost of maintaining safe drinking water in communities that are already among the most underserved in Canada in terms of water infrastructure is rising as the source water itself changes. The fish that support both subsistence harvests and commercial fisheries in Canada's north are responding to permafrost-driven water quality changes in ways that are only beginning to be systematically documented. Arctic char, lake trout, whitefish, and other cold water species that are adapted to the clear, cold, nutrient-poor waters of northern lakes are sensitive to the increases in water temperature and turbidity that permafrost thaw is producing. Some species are being displaced from waters that are warming beyond their thermal tolerance. Others are benefiting from the nutrient enrichment that permafrost carbon brings to previously oligotrophic, nutrient-poor waters. The net effect on northern fisheries, which are a critical food source and cultural foundation for many Indigenous communities, is a complex and ongoing reorganization that will take decades to fully understand. The caribou herds of Canada's north, which have been the cornerstone of subsistence cultures across the subarctic and Arctic for thousands of years, are themselves in serious decline in multiple regions. The Bathurst herd, which ranges across a vast area of the Northwest Territories, and Nunavut, has declined from a peak of approximately 470,000 animals in the late 1980s to fewer than 20,000 by the late 2010s. The Beverly herd, once one of the largest caribou populations in the world, has declined so severely that its status is now disputed, with some researchers questioning whether it continues to exist as a distinct population at all. The causes of these declines are multiple and interact with each other in complex ways, but the permafrost-driven changes in the tundra landscape including the expansion of shrub vegetation that makes travel more difficult, the formation of thermokarst areas that create obstacles to traditional migration routes, and the changes in the timing and distribution of the vegetation that caribou depend on are among the contributing factors. For the Dene, Inuit, Cree, and other First Nations whose cultures are built around the caribou, these population declines represent a crisis that is simultaneously ecological, cultural, economic, and spiritual. The right to harvest caribou is not simply a matter of food supply. It is embedded in legal agreements, cultural practices, spiritual relationships, and social structures that have been maintained across generations. When the caribou are gone from an area, it is not only the food that disappears, it is a way of life, a framework of meaning, and a connection to the land and its history that cannot easily be replaced. The story of what is happening to Canada's permafrost is, in the end, the story of a country confronting the full complexity of its relationship with a landscape that has always been, in the most fundamental sense, beyond its control. Canada is a large country with a small population, most of it clustered in a narrow band along the southern border, looking out at a vast and largely unpopulated north that has been the source of national identity and national resource wealth, but that has rarely been the subject of genuine national attention or sustained national investment. The permafrost crisis is forcing a different kind of attention, one that cannot be satisfied by resource extraction or romantic mythology. It requires real knowledge, real resources, and real engagement with the people who live there and with the scientific complexity of what is happening. The ice is speaking. The ground is opening. The past is entering the present. Canada's answer to this moment will be one of the most consequential chapters in the history of this country, and one of the most significant contributions, or failures to contribute, to the larger story of how human civilization responds to the environmental consequences of its own choices. The permafrost will not wait for politics to catch up. It is moving at its own pace, which is now faster than anything in its history, and the window for an adequate response is measured not in generations, but in years,